Welcome to the session on radians, Radian Measure Part 2. The objectives for this session are to know exact values of angles measured in radians. In the previous session, we noted that one of the most common measures of angles is in degrees. 1 degree equals 1/360 of a revolution of a circle. Angles can also be measured in radians, and pi radians equals 180 degrees. We are now going to find trig ratios using an equilateral triangle. We have done this previously, however, it's been done with degrees and we're now going to transition to radians. So we begin by considering an equilateral triangle ABC with side length 2 units. Each of its angles has size 60 degrees. If we drop it perpendicular from A to D, the centre of BC as shown, then the side length BD has length 1 unit. The angle now created, BAD, is equal to 30 degrees. And using Pythagoras, we can find that the side length AD is √3 units. We are now also going to highlight some important angles in radians. We know that pi radians equals 180 degrees, and therefore we can deduce that 30 degrees equals pi over 6 radians, 60 degrees equals pi over 3 radians, and 45 degrees equals pi over 4 radians. So in our triangle, we have that 60 degrees equals pi by 3, as shown, and 30 degrees equals pi by 6, as shown here. We are now going to continue with this process using radians instead of degrees. From this triangle, we are able to deduce these trig ratios. Let's talk through each of them in turn. First, consider sine pi by 6. We're going to use the formula sine A equals opposite over hypotenuse. So in our triangle, we have sine pi by 6, which is sine A, equals opposite, which is 1, over hypotenuse, which is 2. And now for sine pi by 3. In our triangle, we have sine pi by 3 equals opposite, which is √3, over hypotenuse, which is 2. Now we're going to go to cos. Cos A equals adjacent over hypotenuse. So again in our triangle, we have cos pi by 6 equals adjacent, which is √3, over hypotenuse, which is 2. Cos pi by 3 equals 1, the adjacent, over 2, the hypotenuse. And now for tan pi by 6. We're going to use the formula tan A equals opposite over adjacent. So again in our triangle, we have tan pi by 6 equals opposite, which is 1, over adjacent, which is √3. And of course, 1 over √3 equals √3 over 3. And finally, tan pi by 3 equals opposite, which is √3, over adjacent, which is 1. And of course, √3 over 1 equals √3. We are now going to consider the trig ratios which can be found from an isosceles right-angled triangle. So let's consider this one. The side lengths are 1 unit each, and therefore the hypotenuse is equal to √2 using Pythagoras. Since one angle is a right angle, we have that the other two are both 45 degrees, since we're considering a right-angled isosceles triangle. Again, let's consider 45 degrees in radians. And of course we have that 45 degrees is pi/4. So we're going to use pi/4 in our triangle. Now let's show how we come about these particular trig ratios that you can see on your screen now. So let's first consider sine pi/4. We're going to use the formula sine p equals opposite over hypotenuse, which is sine pi/4 equals opposite, which is 1, over hypotenuse, which is √2. And now for cos p equals adjacent over hypotenuse. So we have cos pi/4 equals 1 over √2. And finally for tan, we're going to consider the formula tan p equals opposite over adjacent. So tan pi/4 equals opposite, which is 1, over adjacent, which is also 1. And of course 1 over 1 is equal to 1. Here's a summary of the trig ratios using radians. We're now going to take a look at the cast diagram. This shows which trigonometric ratios are positive in which quadrant, as shown here. Consider the angle theta as shown. It's going to create another angle theta in the opposite quadrant. So if this angle is theta, then if we're considering the direction anti-clockwise, then the angle that's being made with the other angle theta is actually pi plus theta. And this new angle theta is actually pi minus theta, again, if we're considering the direction anti-clockwise from the x-axis, or the positive x-axis. And finally here we have 2 pi minus theta. Again, we're measuring anti-clockwise from the positive x-axis. So in the quadrant where it says sine positive, we have sine pi minus theta equals positive sine theta, cos pi minus theta equals minus cos theta, since only sine is positive in that quadrant, and tan pi minus theta equals minus tan theta. And in the next quadrant, as highlighted, we have sine pi plus theta equals minus sine theta, since only tan is positive in that particular quadrant. We also have cos pi plus theta equals minus cos theta, and of course we have tan pi plus theta equals tan theta. And finally, in the cos positive quadrant, we have that only cos is positive here. So sine 2 pi minus theta equals minus sine theta, cos 2 pi minus theta equals cos theta, and tan 2 pi minus theta equals minus tan theta. So here's a summary of our key results. It is also possible to use the symmetry properties and periods of graphs of sine, cos and tan to find the above results. Here's a summary of the results from the cast diagram, highlighted in a different way in order to help us access them in our examples. So let's consider this example, as you can see on your screen. Pause the video and have a go. Press play when you're ready to view the solutions. Let's take a look at part A first. We are required to find the exact value of sine 4 pi by 3. So let's solve this. Here's a sketch on the cast diagram of the angle 4 pi by 3. 4 pi by 3 is equal to pi plus pi by 3. We've split it up in this way so that we can use the formulas that are now highlighted on your screen. Since we're considering sine, we need to consider the sine formula first, which is sine pi plus theta equals minus sine theta. And therefore, since we're considering sine pi plus pi by 3, our theta is equal to pi by 3. And therefore we can conclude that sine pi plus pi by 3 equals minus sine pi by 3. Now from our trig ratios, we know that sine pi by 3 equals root 3 over 2. And therefore minus sine pi by 3 equals minus root 3 over 2. And so we have that sine 4 pi by 3 equals minus root 3 over 2, as shown on your screen. We are now going to look at solving part A using a different method. In particular, using the symmetry properties of a graph. In this example, we're looking at sine. So here's a sketch of y equals sine x. As you can see, we've highlighted 4 pi by 3 on the graph. The value of sine 4 pi by 3 is negative. By symmetry, you should hopefully be able to spot that sine pi by 3 is going to give the same positive numerical value as sine 4 pi by 3. And therefore, sine 4 pi by 3 equals minus sine pi by 3. And since sine pi by 3 equals root 3 over 2, we have that minus sine pi by 3 equals minus root 3 over 2. And therefore, sine 4 pi by 3 equals minus root 3 over 2. Now let's take a look at part B. We are required to find the exact value of cos minus 5 pi by 4. So let's solve this. On the cast diagram, you can see the angle minus 5 pi by 4. This is going in a clockwise direction from the positive x-axis. This is the same as 3 pi by 4 in the anti-clockwise direction as shown. And therefore, cos minus 5 pi by 4 equals cos 3 pi by 4. Now since 3 pi by 4 equals pi minus pi by 4, we have that cos of 3 pi by 4 equals cos pi minus pi by 4. The relevant quadrant in the cast diagram has now been highlighted. These formulas are derived from this quadrant, and this is why we've split pi minus pi by 4 in this way. In particular, we have that cos pi minus theta equals minus cos theta, and therefore cos pi minus pi by 4 equals minus cos pi by 4. Since cos pi by 4 equals 1 over root 2, we have that minus cos pi by 4 equals minus 1 over root 2. And therefore, cos minus 5 pi by 4 equals minus 1 over root 2. This brings us to the end of this session. If you have understood its contents, you should be able to know exact values of angles measured in radians. Thank you very much for listening. To understand this topic in greater depth, do attempt the exercises in your textbook related to this topic.